So here we're asked to solve for the equation describing the displacement of the cart over time, so x of t, if the cart is released from rest when pulled to the right by 0.2 meters. We have a forcing function which is applied onto the cart, so we can see that in the diagram here, and we're given the values for the mass, damper and spring. Alright, so just a bit of a pre-warning, this question is going to be a little bit long, in that it's going to end up being a non-homogeneous ODE that we need to solve. So, the first step is going to be to actually get that differential equation out of our system. So we're going to get that by drawing a free body diagram of the cart, and by summing forces being equal to mass times acceleration, we should be able to get a differential equation which includes x, our displacement of the cart, and time t. So let's scroll down a little bit. So I'm going to isolate the cart from everything else that it's attached to because it's a free body diagram. Drawing on the forces, so we know that there's going to be a weight associated with the cart, mg, and it's on a horizontal surface, so there's going to be a normal force acting back up. And I'm just going to condense it into the one force. Really that's because these aren't going to impact upon the movement in the horizontal direction that we're interested in. Alright, so we also have this force F of t, that's the applied one that was given in the question. So up the top here we were told that that applied force is cos of 3t. Alright, so the other thing that we're going to have is, if I'm going to pull this cart to the right, what's going to happen is the cart is going to accelerate in that direction. So I'm going to call this the ma, mass times acceleration, or you can write this alternatively as mx double dash, because acceleration is the second derivative of displacement. Okay, so this isn't a force, right? This is the mass times acceleration, which is why I haven't drawn it directly onto my free body diagram, which only captures the forces. So why I've done this is because I'm now going to assume that because the force is pulling it this way, it's going to accelerate in this direction, and it's going to mean that we're going to have resisting forces back to the left, which are as a result of the damper and the spring which are attached to the cart. So for the damper, we know that the force that it provides is going to be equal to the constant, which is c, multiplied by the velocity that it's moving at. And since it's directly attached to the cart, the velocity of the cart is going to be the velocity that this damper gets moved at. Similarly for the spring, alright, it's directly attached, so if this cart gets displaced a distance x, then the spring is also going to stretch that same distance x. So that's the force from the spring. So I think that's our complete free body diagram. So what we should be able to do now is perform our sum of forces calculation, which is equal to the mass times acceleration. And I'm going to apply this only in the x direction, okay, simply because that's where all the movement is happening. Nothing happens in y. So I'll pop little subscripts on here to remind us. So in the x direction, I have both of these spring and damper forces, and we can see they're in the negative x direction, so we're going to pop them into the equation as negatives. I can also see I have this applied force, and that's in the positive x direction, so it's going to go in as a plus. So I might just take this version of it for now, the f. Okay, we can substitute in this in a moment, and this is the function of time thing, so I'll just drop that and call it f on its own so we don't get confused. And then we have the mass times acceleration part, and we've drawn this to be acting in the positive x direction, so therefore it's going to be positive when it gets substituted into the equation, and I'll pop it in this form mx double dash. Alright, so we should be able to rearrange this equation. So I'm going to leave the force on the left hand side and move everything with x's onto the right. So we can write it as this. And what I'm going to do is, so that it is in kind of standard form, or a more standard form, I'm going to put this force onto the right hand side. Okay, and then we're going to have the left-hand side with all the x stuff and the right-hand side with everything else. And I may as well kind of normalize this front term here. So if I want a 1 in front of my highest derivative, I'm going to divide everything by m. So it'll become mx double dot dividing by m, get that, divide this one by m, we get that, and we also have to divide the right hand side by m as well. So that would be like the standard form, or the general form of my differential equation. Now I can substitute some numbers and some values in at this point. So we were given up in the question what m, c, and k were, and also we've got this cos of 3t. So let's pop all of that information in. So c divided by m ends up being 8 divided by 2, which is 4. And k divided by m is 6 divided by 2, which ends up being 3. And our force function was cos of 3t, m was 2. Okay, so if we wanted to, we could write this as 0.5 cos of 3t as well. Alright, so now we're at the point where we can probably try and have a go at solving this equation. So we can see that it's a second order equation, and it's going to be a constant coefficient second order equation because we just have numbers out the front of each of our terms on the left hand side here. And we can see the right hand side is a function of t. So the process we can use to solve this, I summarized up here, and there was a recap video going through it in a bit more detail. But essentially we go through these kind of 3 steps in order to get our solution out. So the first step is looking for the homogeneous part of the solution. So we're going to try and find the roots to the characteristic equation, and then we're going to use this to select what our homogeneous solution should look like. So coming back down over here, homogeneous just means that the right hand side here is set equal to 0. So just pop in here as a reminder. So the solution, or the equation I should say, that we're looking for a solution to, we set this to be equal to 0, and then we should be able to get our characteristic equation out. So remember, we introduce r as a variable, and the power of it corresponds to the number of derivatives associated with the term. So this here becomes the characteristic equation. And what we need to do is get out the roots of that equation. You can see it's a quadratic, so we can use the quadratic formula in order to solve. So a is the number that's out the front of our squared term, so it's 1. B is the number out the front of the constant term, so that's going to be 4. And c is just the number that floats out the end, which is 3. So let's apply our quadratic formula. So substituting into this, alright, so what ends up happening here simplifies down to the square root of 4, and square root of 4 is an easy one, that's just equal to 2. So we're going to end up with 2 solutions falling out of this. So the first one is where we take the positive from that plus or minus sign, and this works out to -1. And then our second solution, which I'm calling R2, is going to be when we take the negative in there, and this works out to be -3. So what we've found is our 2 roots of the characteristic equation, and we can see that they're both real numbers and they're different from each other. So we can describe these roots as being real and distinct or different. Okay. So now if we go back up to our little cheat sheet of instructions, what it told us to do was, based on our finding of this first point, we need to select the form of a homogeneous solution based on the case. So that's from this table here. So we have our 3 different options. We've ended up with this top first option where we have real and distinct roots. So that means our solution for the homogeneous portion of our equation looks something like this. So let's come and copy that down. So xh is going to be equal to c1e to the r1t plus c2e to the r2t. And of course we've just solved for r1 and r2, so we can pop them in. So it's going to be this. And I'll pop xh out the front here. Oh, and we had a 1. So we don't know what C1 and C2 are, at the moment, they're going to be constants. We're going to have to try and find them at the end when we use our conditions for the specific situation. Alright, so that's the first part of our solution complete. So the next bit that we're going to need to do is looking at the particular solution. I'm just going to highlight this because we're going to need to come back and use that again at the end. So coming back up to our list of instructions, alright, in order to get this particular solution, we need to assume what yp is equal to, that's our particular solution, based on the guessing table. Okay, so if we come down here, this is the guessing table that we need to use. And what we're going to look at is what's on the right hand side of our differential equation. And this is the regular version, not the homogeneous one. So this was our normal or original ODE that we wanted to solve. And we look at the right hand side here, we can see it's like a cos function. So coming back over here, if we look down here, we can see that one of the options in our list is a cos function. So that means that we're going to want to read off this version of our yp in order to continue solving. So we're going to pick that up in a second. And what we're going to do with it is assume this yp and put it into the left-hand side of our non-homogeneous ODE and solve for the constants that fall out. So you can see there's a constant of a capital A and a capital B here. Those are the ones that we're going to try and find. The B that's inside the brackets here is going to be copied across from whatever our right-hand side was in the actual question. So in our case, the little b here was 3t. Was 3, so we can put them in as 3t for each bracket there. Alright, so let's come down over here. Oh, so many steps. So rather than call it y, since we're looking in the x direction, I'm going to call it x. And the general form that we were told was a cos, remember we said we're going to use what was in our right hand side, so 3t plus b sine of 3t. Ooh. So we're going to try and substitute this expression up into that non-homogeneous ODE, this one here. So in order to do that, we're going to need x, x dash, and x double dash. So let's take these derivatives so that we're going to be able to just substrate in a moment. So taking our first derivative here, what it's going to become is a stays out the front. We know that cos goes to negative sine when we take the derivative, and we copy out the bracket, and then we need to multiply by the derivative of what's inside the bracket. That's the chain rule. So the derivative of 3t with respect to time is just going to be the 3. So plus, again, taking the derivative, b stays out the front, sine here goes to cos, copy out the bracket and multiply by the derivative of the bracket. So we can write this a little bit nicer as something like this, plus 3b, it's going to be cos of 3b. Alright, so let's take another derivative, the second one. So here, the constant stays out the front, sine goes to cos, and multiply by the derivative of what's inside the bracket. Applying the same thing here, we get that. So again, we can clean this up a little bit, and we end up with this for the answer. Oh, it's going to be negative. Yeah. Alright, so the non-homogeneous equation from before, I'll just copy it out to remind us. Again, non-homogeneous just means that we're not considering this to be 0. So what we're going to do is substitute all of these expressions into the equation, and we should be able to then solve for the a and b constants. So the second derivative is this one here. And then we've got 4 times the first derivative, okay. Alright, and then we have 3 times the normal original function or whatever. Plus b sine 3t. And we know all of this has to be equal to the right hand side, so I'll just pop that underneath since I've kind of run out of space. Alright, so what we're going to need to do now is expand out all of the brackets on the left-hand side of the equation. So the first one's easy, it doesn't really have any brackets. Alright, then we're going to get negative 12a plus 12b. And then we've got 3a and 3b. And again, all of that has to be equal to the right-hand side. So what we're trying to get out is what a and b are equal to. So I'm going to try and factorize the cos 3t's out and the sine 3t's out. And what we should find then is we can equate whatever the constant is out the front of it over to what's on the right-hand side of the equation. So let's start with factorizing out the 3t. So we've got a negative 9a that sits there. This one we'll leave out because there's sine as well. We've got plus 12b for the next one, and then we've got a plus 3a. So now let's do all the ones with sine. So negative 9b minus 12a, and then plus 3b on the end here. And all of that has to equal cos of 0.5 cos of 3t. Alright, so we can do a little bit of putting this together. So we can simplify this one here to be negative 6a plus 12b. And the second bracket can be simplified to negative 6b, minus 12a. Alright, so in order to work out these constants, what I can say is that the cos of 3t, whatever's out the front of it, or in this case out the back of it, has to be equated back to the 0.5 we see here. And what we're going to find is that the constants here can be equated to, I can write this as 0 sine 3t because we have 0 of them on the right hand side. So therefore 0 is going to have to equal this part of the equation. So let's write out this. It's going to be simultaneous. So this had to equal 0.5. And then this stuff here had to equal 0. So I'm going to start by rearranging this one here to get b equals. So if I swing this term to the other side, we end up with that. And then b is going to equal 12a divided by negative 6, which leaves you with negative 2a. So if we now substitute this back up into the other equation to solve simultaneously, so the b is getting replaced with this negative 2a. If we put all of this together, we end up with negative 6 minus 24a, which overall is negative 30. So this leaves a as being 0.5 divided by negative 30, which is the same as negative 1 on 60. So now that I know this, I should be able to come back over here and get out what b is equal to. And this simplifies down to 1 on 30. So these are the two constants within the particular equation that I was looking for. If I scroll back up, this is what x of p is equal to. So we can now pop in a and b as the actual numbers. So that makes x of p equal to negative 1 on 60. Cos of 3t plus 1 on 30 sine of 3t. Alright, and that concludes the particular section of our solution process. So coming back up to where we were looking through the steps, we've now completed this. So we're up to the third part, which is looking for the overall solution where we add the homogeneous and particular parts and then apply the conditions to find the constants. So let's just think about these conditions. They're going to come from the text that we had back at the beginning. So one condition is going to be that the cart is released from rest. Okay, so what that means is that at time equals 0 when it's released, its velocity is going to be 0 because it's at rest. Okay, so that's one condition we can use. The other one is it's released when it's pulled to the right by 0.2 meters. Okay, so it's already kind of displaced at the beginning. So that forms a second condition that we can use. So let me come down the bottom here, and I'm going to write out those conditions. So this is the overall part of our solution. So the first one was at time equals 0, the velocity, so that's x dash, is equal to 0. And the second one was at time equals 0, it's pulled to the right by 0.2 meters. So that means the position x is equal to 0.2. So we're going to use these in the overall equation, which remember was x is equal to the homogeneous plus the particular. For the homogeneous, we got it to look like this. And for the particular, that's what we just figured out here. Okay, so now what we're going to do is use each of these conditions. So I might start with the second one here. Okay, that's because it's in terms of x, and I've got this equation in terms of x. Okay, so let's start by substituting it into the equation. So x is going to be 0.2, and anytime we see a time, it's going to go to 0. And this is what we get. Okay, so we can do a bit of simplifying. Anything to the power of 0 is 1, so that's going to go away. Got it happening here too. Cos of 0 is equal to 1, so we're just going to be left with the negative 1 on 60. And sine of 0 is equal to 0, so in fact this whole one is going to disappear. So the equation just becomes this. Ended up still with my two unknowns appearing in the equation, so we're going to have to solve it simultaneously with that second condition. So in order to prep for that, I'm going to rearrange for one of the unknowns. I'll go for C1, so we can write it like this. Okay, and we're going to be able to sub that into the second equation we get out. So let's use our, first condition now. This one back up here. I should rewrite that. So this was actually our second one that I used. The first one, we can see that that's written in terms of x dash, the velocity. So in order to use it, we're going to need to write out our equation here in terms of velocity, and we can get that from taking a derivative. So x dash, okay, taking our derivative. This one here, the constant stays out the front. The derivative of e to the x is e to the x, but then we need to multiply by the derivative of what's up in the exponent, and that would be like the negative 1. Following the pattern here, we're going to get c2 times the exponent times the derivative of what's up here, which is negative 3. This one, we're going to get the negative 1 on 60 out the front. Cos goes to negative sine, and multiply by the derivative of what's inside the bracket. And then for this last bit, sine goes to cos, multiplied by 3. So that means that our velocity equation becomes this. It's going to be plus 3 on 60 is the same as 1 on 20. And then 3 on 30 is the same as 1 on 10. Alright, so now let's actually go ahead and put this condition in. Alright. So the velocity is equal to 0 at time is equal to 0. Alright, so again we've got the e's to the zeros, which are equal to 1. Sine of 0 is equal to 0, so it knocks that whole term out. And cos of 0 is 1. So we can rewrite this like so. Now we have our two equations that have the same two unknowns, so we can solve them simultaneously. So if I substitute this equation into the second one, so C1 is getting replaced. It's going to look like that. You can see that C2 is the only unknown in the equation. So if you move everything with C2 to one side, everything without to the other side, what you can find is that C2 comes out to approximately this. Okay, and then once you know C2, you can go back and substitute it into the equation with C1. So 0.2 plus 1 on 60 minus that C2 value that we just found, and C1 comes out to 0.275. The final step is just to take this information and substitute our constants back into the equation for x. Okay, so it's this one here. We now have this and this variable. So that makes our final answer, x equals 0.275 e to the negative t minus 0.0583 e to the negative 3t, and then the last part of the equation that was from the particular solution we already had. Alright, and all of this, it's a displacement, would be measured in meters since that was the units we were working in. So that's all there is for this particular question in terms of finding that ODE, and it's a very, very long process, as you can see. So the only other thing to mention then is that you can check your solution in MATLAB. So what I've done here is set up a time vector, got these constants, and I've written out the equation for displacement x and also the one for velocity v, and I've plotted them. So if we look at first the displacement equation being plotted, what we can see is that it's starting at 0.2, which is what we were expecting. So we've definitely met that condition, and you can see that it's following this kind of sine, it was a cos wave that we had as our input function, or applied force function, so it kind of looks like what we would expect over time. This one here is the velocity versus time, and of course the condition that we had on it was that velocity at time equals 0 is equal to 0. So again, we can see that we've met that condition, so there's been no silly mistake that's happened in the solution. And again, the velocity kind of goes back and forth over time as well, simply because our little cart is getting pulled left and right, so it's going to have a velocity that alternates in terms of direction. So that's all there is in terms of this video.